Hi, Dr. Anthony Revis, and this is Watch Me Work It Again. Um, we're going to take a look at a thermodynamic calorimeter problem. All right, so here we go. Here it is. If 0.315 moles of hexane is combusted in a calorimeter containing 5.65 liters of water, calculate the molar heat of combustion of hexane in the water. Temperature rises 55.4 degrees C. And so we have the heat capacity here. Now, a couple of things you want to keep in mind here. When you see a problem like this with liters of water, you want to remember that water has a density of 1 gram per mil, or 1 gram per cc, or 1 gram per centimeter cube. Doesn't matter how you think about it. But when it comes to these types of calculations, this is a direct substitution for grams. So the point I'm making here is when you see liters, you think grams. But now this is liters, okay? So here we have to keep that in mind when we do this calculation. So in terms of grams, that's 5.65 liters. So what we know is we have 5,650 grams, okay? Because that's, all right, you get it? So that's direct conversion from milliliters, all right? So we can start there, or you can set up the old calculation to get it. So that's one of my givens. So what do I know? I know that this is basically delta H, or the heat, is equal to ms delta T, okay? And so what I'll do here then is I will take my mass, which is 5,650 gram. So I'll take my mass times the specific heat of 4.184 joule per gram degrees C, times the delta T, the change in the temperature here. Oh, there it is right there, 55.4. It already did it for me. And so if I take this and I punch this number, through just right here, I'm going to get 1,309,633.84 joules. And typically this is changed to kilojoules. Let me just go ahead and figure my sig figs here as well. So I have 3 sig figs. So my sig figs is going to be, if I write this really long joule number, it's going to be 1 like this, right? 0, 0, 0. And typically we'll do that in terms of kilojoules. When you get a number that large, you'll just say, and so this is joule. So you'll go time joule to kg. And so 1 is equal to 1,000, which means that your final answer is 131 kilojoules. That's my square-in answer for that. So that's how you do these. This is basically take it, plug in the values, and run the numbers. And if you have to convert them from joules to kilojoules, you just do that direct conversion, okay? Let's do another one here. Now, this one's a little bit more involved, requires a few more steps than the previous one did, okay? So now, in this particular case, what we have is the following problem. Ready? We'll walk it through and try to label up as best we can. Watch me do it. Here we go. When a 0.235 gram sample of benzoic acid is combusted in a calorimeter at 3.65 degrees C, a 3.65 degrees C rise in temperature occurs. Okay, so that's one event. Event number 1. Got it? Boom. Next event. When a 0.305 gram sample of citric acid is burned, a 1.83 degrees temperature rise is observed. Got it? All right, that's the second event. Now, watch this. This is important. So we have event number 1. I'm going to label it right above what's the species, and event number 2. Now it says if the heat of combustion of benzoic acid, that's event number 1, equals this value in kilojoules per gram, okay, in kjoules per gram, all right? What is the molar? So this is molar, so this is the moles. Heat of combustion of citric acid. So what we're essentially doing is, number 1 is a known, and number 2 is an unknown. So that's how we'll treat these. In other words, I can get all my values from this one, but I'm missing a value here. But but what I'm missing in number 2 can be obtained through number 1. That's the point. So when you see a problem like this, one's the standard, one's the unknown. Run calcs on the known, use a value from the known, and plug it into the unknown. And that's what we're going to do. So watch us do this. Ready? So here's what we know. We know that for process number 1, the heat, okay, all right, the heat of combustion, the Q, or the delta H, equals 26.38 kilojoules. You see it? I'm just reading it right from the problem. But here's what I also know. It's a heat of combustion. I happen to know that combustion is an exothermic process, so I must assign it a negative value. Now I can do this at the end. I can run it through and get the absolute value, then make the interpretation, but I prefer to do it up front. This is what I know, okay? All right, I know then, okay, that I can now calculate the amount of heat so that I can use it to standardize my calorimeter. In other words, what I know is the following, all right? I know that the heat, okay, of my calorimeter of process number 1, the heat equals the heat capacity, not specific heat, the heat capacity of the device times delta T. That's known. Okay. So what I'm going to do is calculate my heat capacity of this device, and then I'm going to use that to solve my unknown. So my device heat capacity then equals, and I'm going to just keep it right here, C is going to equal Q divided by delta T. Okay. All right. With me so far. Okay. So let's finish a few calculations here then. Ready? I know Q, it's a lot to do, is minus 26.38 kilojoules per gram. But I just need to know what that actual heat is, not per gram. So what I'm going to do is I'm going to find this value here. So I'm going to find my Q for this process equals minus 26.38 kilojoules per gram times my grams for this device, 0.235. I tell you what, I think I'm going to write that a little cleaner. Okay, let me erase that, and I'm going to remove that back just a little bit. See if I can make that a little cleaner for you and explain it to you one more time. Ready? There's a lot going on here. So let's do that again. This is the heat capacity, okay? And this is kind of a standard here. This is per gram. So in my process alone, the amount of heat in my process is the amount of heat per gram times the grams. That'll tell me how much heat is generated in this device, in this unit, in my process. This is grams. If I run that number through, I get minus 6.20 kilojoules. So now I'm going to take this and put it in here so I can standardize this, right? And once I standardize that, I can use it. Okay, ready? So now I'm going to take that value, negative 6.20 kilojoules, divided by my delta T, which is 3.62. There it is, 3.62 degrees C. And this is going to give me a heat capacity for that device. And so now that device now has a heat capacity of 1.71 kilojoules per degree C, something you've seen before, right? That's my heat capacity. I had to do all this just to get a heat capacity. Now, because I couldn't look it up on a table. Typically, you can look these up on a table. Now I have my heat capacity. Wow, a lot of work to get around to this. Now I can move on to process number 2. For number 2, I know that my heat now, same type of calculation, is going to be C times delta T. I now know C is 1.71. Okay. All right. And by the way, I don't need the minus sign here. Okay, no such thing as a negative one. Okay, this is just the heat, and I did this in terms of to show you it's exothermic. Okay, but I need an absolute value to do the rest of my calculation. So I'm going to take that right out. So we have 1.71 kilojoule per degree C times delta T. Delta T in this particular case, I believe is 1.83. In fact, it is 1.83. And when I punch that through, my heat for this is 3.13 kilojoules. By the way, you wouldn't have heard a thing by leaving the negative sign in, just to let you know that. It just tells you it's minus, but we typically don't report a negative value for the heat capacity. It just is an absolute value. So here we get this value for the heat, and that's how much heat is generated. But the question asks you to tell me how much is generated per mole. And since this is an exothermic reaction, so let's just do it. So my combustion reaction is going to be this. My final answer in kjoules per mole, and that's what it asked for, will equal, take the, that's a Q I'm trying to write, Q. And so I'll take the kilojoules, 3.13 kilojoules, and I will divide it by the number of moles that I have. All right. And I'll have to do the math here. And so we know that we have the grams, which is 0.305 grams times bar grams per mole. This is from the periodic table. This is going to be 192.1 gram per mole. Getting a little messy, but that's okay. So this is going to give moles on the bottom, and all of this works out to give me When I punch all these numbers through, I get 1970 kg per mole. And since it's, so that's my answer, but since it's exothermic, I'm going to report it as an exothermic reaction. And there you have it. Okay, so what's the key to doing this type of problem is this. Recognize there's two problems. One is to get C. The second is to use C. And if it said per mole, then you simply are converting to moles by using the molar mass. Is what we did on the bottom here. Okay, so that's how you work that type of problem.